All right, grade 11 chemistry. Today we're talking about percent composition, but first we're going to do a little bit of a yields review because that's really a big part of the third unit, the stoichiometry unit. So we're going to do a yields review first, then we'll talk about percent composition, and we'll do some percent composition practice problems. Relatively simple video today, just that one thing about, excuse me, percent composition. So put that away. Here's a question. We have methane burning. CH4 is methane, O2 is oxygen, makes CO2 and H2O. So the question is, if I have 25 grams of methane and 25 grams of oxygen, the first question is, what is the limiting reagent? The second question is, how much CO2 can I make? And the third question is, how much unused reactant, like whatever we have left over, whether it's the methane or the oxygen, how much of it will remain in terms of how many grams of it will remain? So kind of a complicated three-step question here, but let's get started with what is the limiting reagent. What I've done is I've written it out here already, and I used my periodic table, and I worked out the molar mass of CH4 and the molar mass of O2. As you can imagine, for CH4, it was like carbon is 12.01 grams per mole, that's from my table, and hydrogen is 1.01 grams per mole, but there's 4 of them. That's 4.04 grams per mole, and then you add the 12.01 and the 4.04, you end up with the 16.05. The oxygen, each oxygen is 16 grams per mole, and if I multiply it by 2, I get 32.00 grams per mole, and that's what I have up there. So, it did the grams per mole, they're up there in green. And then the question says we have 25 grams of CH4 and 25 grams of O2. So remember, our general rule is that we can't compare two chemicals unless we're working in moles. So what we should do is convert these to moles first, and then we can compare. So let's divide. Right, we divide by the molar mass, or what we can do actually, we'll do it the other way with the conversion factors. Multiply by what goes on the bottom? Well, grams goes on the bottom. Grams goes on the bottom, so 32.00 grams for 1 mole. And this one is 16.05 grams for 1 mole. That tells us that we divide. Or you can remember that you divide. There's a bunch of different ways to remember this stuff. Time for a calculator. Get our calculator out. 25 divided by 16.05 is 1.56 moles of CH4, and 25 divided by 32, 0.78 moles of O2. Okay, now there's 2 O2s and 1 CH4 in my equation. So what do I do with that? Well, there's a few different ways to do this. Perhaps the easiest is just to figure out exactly how much CO2 I can make. Right, this is the CO2 up here. I have CH4. 1 CH4 makes 1 CO2. So if I take my CH4 and I do my mole ratio, my CH4 actually needs to be on the bottom. My CH4 to cancel out my CH4, and my 1 CO2 has to be on the top, so I can make 1.56 moles of CO2 on top. Right, remember that was actually one of our questions. Our question B is how much CO2 can you make, so it makes sense that I might want to figure out how much CO2. That's how many moles of CO2 I can make there. Now the oxygen, I want my oxygen on the bottom and my CO2 on the top, because the oxygen is going to cancel out the oxygen. Right, we want to cancel those because the fractions work that way. And I have a 2 in front of my O2, so it's 2 O2 and it's 1 CO2, so I'm actually going to cut that in half. So 0.78 divided by 2, 0.39 moles of CO2. So why did I do this? Well, it tells me that with 25 grams of CH4, I can make 1.56 moles of CO2. With 25 grams of O2, I can make 0.39 moles of CO2, which tells me then 2 things at once. It actually helps me solve A and B in my question. Let's go jump back to the question. The question was, which is the limiting reagent is A, and B, how much CO2 can I make? Well, I just answered both of those, right? The O2 is the limiting reagent. O2 is the limiting reagent, and I can make 0.39 moles of CO2. 0.39 moles of CO2. So, this is the usefulness of these conversions. 0.39 moles of, CO2. Okay, so that's your 0.39 moles of CO2. O2 is the limiting. Now the last question is the one that takes a little bit more work. So the last question here is how much unused reactant will remain? Well, the unused reactant is this guy. It's the CH4, right? We're not going to use all of the CH4. So we can kind of rewrite that question as if I make 0.39 moles of CO2, which as I worked out, I make 0.39 moles of CO2, how much methane do I use? All right, that's the first question, methane. That's the first question we should ask ourselves, because if we figure out how much methane we use, we can take it away from our initial amount of methane, and then we can work out how much is left over. So that requires a conversion. 0.39 moles of CO2. I'm going to take it through our mole ratio. Now CO2 is on the bottom. We want to cancel CO2, and we want to figure out how much methane, which is CH4. All right, it's a 1-to-1, so it's 0.39 moles. 0.39 moles of methane. And then I want to figure out how much that's going to weigh. So let's figure out how much that's going to weigh. So we take our 0.3, I'm going to change colors here. Take our 0.39 moles of methane of CH4. I want to figure out how much it weighs. We know that it's 16.05 up here, 16.05 grams per mole up there. We got to figure out if we're multiplying or dividing. Well, we can use our conversion factor thing. Right? Moles is up here. We want moles on the bottom, and that's always per 1 mole, grams per mole. So we're going to multiply by grams per mole, and we're going to get some kind of number. So 0.39 times 16.05, 6.26 grams. 6.26 grams of CH4. We're going to use 6.26 grams. We started with 25 grams. We just figured out that we use 6.24 grams. So to figure out what's left over, which remember, that was the question, how much unused reactant will remain, to figure out what's left over, you just take your 25 grams up from up here, 25 grams, CH4, take away your 6.26 grams, that's what we used, take it away, 6.26, and we get 18.74 grams left over. We still have 18.74 grams of CH4 remaining. So yeah, we don't use a lot of our methane. That's a basic kind of the basic flow of a yields question I can ask about. You can see that I can ask about what's the limiting reagent. I can ask you to do a stoichiometry to figure out how much of something you can make, and then the most complicated kind of question we can get to is how much unused reactant will remain, which requires multiple conversions to get. But yeah, that's our yields review. Our next section is going to be percent composition, so I'm going to pause and get that started. So let's talk about percent composition. Percent composition comes from various analytical techniques. One of them is diagrammed here in the textbook. It's called combustion analysis. Combustion analysis, there's the name for it. This is used to identify kind of organic samples. What they do is they add oxygen, there's the sample, they heat it up and it burns, and then they can pull out water, they can pull out carbon dioxide, they can pull out other things, they can work out how much carbon, how much hydrogen, how much whatever was there in mass, by mass. So that's where it comes from, and it comes from analytical chemistry. Analytical chemists, they do tests to work out the mass of each element. Combustion analysis is just one example of one of those tests. And here's kind of an example. If a sample contained 31.998 grams of oxygen and 4.032 grams of hydrogen, right, we can write those numbers out. 31.998 grams of O2 and 4.032 grams of H2. You'd end up with something like that. And it wouldn't really be O2 or H, I guess it would just be oxygen and hydrogen, right? Just pure oxygen and pure hydrogen. You could work out a percent composition from this. The whole compound, if you add this together, right, the whole compound together, 31.998 plus 4.032 is 36.03 grams total. And then you could work out the percentages of the composition. So you can have a look at, if it's the hydrogen, it's the percent hydrogen, it would be 4.032 grams of hydrogen over the total, the 36.03, just like any kind of percent. It's whatever you get over the total. And you'd end up with some number, 4.032 divided by 36.03 is 11.2%, right? 11.2%. And the percent oxygen, you've got two options. You can either do the same thing, 31.998 grams of oxygen over the total, 36.03 grams of total, or there's a shortcut you can take because it's only oxygen and hydrogen, so it's going to be 100%. So you could do like 100 minus 11.2. Well, let's prove that that we get the same number. 36.03. Yeah, 88.8% oxygen and hydrogen. So it's by mass, and you can see that they add up to 100. The percentages should add up to 100. It's a good little self-check that you can do when we're doing a percent composition problem. But that's the kind of math that it takes to make a percent composition. And it's a measure of what you're interested in over the total mass, and it's a percent. And you see mass of element over total mass of compound. And that's what you see me doing here. The mass of the hydrogen over the total mass. The mass of the oxygen over the total mass. Notice that that's the same number in both times. It's the total mass. Nowhere did I never do hydrogen divide by oxygen or anything like that. That doesn't make sense. We just want it as a percent of the total. So that's that. Yeah. So let's do an example problem of determining a percent composition, and I'm going to pause for a second to get that set up. So there's this famous assertion that was made by Richard Feynman he said most of a tree comes from the air. And the reason that he said that was because trees absorb CO2 from the atmosphere. They take in water from the ground, but they do take in CO2 from the atmosphere, and they use that to make tree stuff, right? They make wood out of it and all kinds of other things. So as an example problem for percent composition, I thought it might be fun to figure out what percentage of a tree's mass comes from the air versus coming from the ground. And here's a photosynthesis equation. I'm going to bring my thing down here. All right, CO2 and H2O go in. This is water. So this is glucose. This is what actually makes up the tree. Out goes oxygen. Out goes water as well. So some water comes in, some water comes out. More water comes in than comes out. Within the C6H12O6, which is the glucose, the carbon and the oxygen are coming from the CO2 that comes in. So the carbon and oxygen come from the CO2, and the hydrogen comes from H2O. So if we work out what percent of the glucose, what percent of the tree's mass is carbon and oxygen versus what percentage of it is hydrogen, we could work out how much of the tree comes from the air and how much of the tree comes from the water. So let's try that out. Let's actually do that. Right? We'll use the same kind of math, the same kind of logic, but this time we've got C6H12O6. Right? That's C6H12O6. 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 So every time we do it, right, the percent carbon, for example, would be the mass of carbon over the mass total, right, over the mass total. So what we need is the mass of the carbon and the mass of the total. And all we have is the formula. So how do we do this using only the formula? Well, we always have a periodic table available. Right, we've always got this guy. It's always available to us. And it has masses. It has the mass of carbon, it has the mass of hydrogen, it has the mass of oxygen. So I can get the mass of carbon, but then I also need the mass of the total. So I'm going to have to get the mass of C6H12O6. I'll need the mass of the carbons in the C6H12O6 and the mass of everything else. So I'm going to set that up. Let's set that up. All right. And I'm going to set it up in a typical kind of figuring out the molar mass. I've got C6, H12, and O6. Right? C6 is going to be 6 times 12.01 grams per mole, because that's what my table says for carbon, 12.01. I find that in my table. There it is, 12.01. There's 12 hydrogens, and multiplied by 1.01 grams per mole. And I have 6 oxygens, 6 times 16.00 for oxygen grams per mole. And then I'll do the multiplications. This one's obviously 12.12 grams per mole. 12.12 grams per mole. This one would be 96 grams per mole, just multiplying the 6 times the 16. And then 6 times 12, 6 times 12 is what, 72.06 grams per mole. 6 times 12. So that's carbon, hydrogen, and oxygen. And then I can work out a total. I can add these together and get a total. 72 plus 12.12 plus 96.00. So 72, I've got my calculator out, 72.06 plus 12.01 plus 96.00, 180.07, 180.07 grams per mole. That's the total. Right. And then if I want percentages, I would just take each individual atom and divide it by the total. So 72.06 grams per mole divided by 180.07 grams per mole. Oh, did I screw something up somewhere? Oh, it's 12.12, isn't it? 80.18, sorry. 180.18. The wrong, I put in the wrong number in my calculator. 0.18. 0.18 grams per mole. So 72.06 divided by 180.18 grams per mole. Is pretty close to 40%. 39.99%. 39.99%. For the hydrogen, that's carbon, right? For the hydrogen, it would be 12.12 grams per mole divided by my total. You know, I'm actually going to write my total in black. so that we have a visual that it's a total 180.18 grams per mole, divided by 180.18 grams per mole. So the percent of hydrogen is whatever that's going to be. Let's get the calculator out. 12.12 divided by 180.18 is 6.7%. 6.7% oxygen. 6.73, I guess. 6.73% hydrogen. And then for the oxygen, you've kind of got two options. You can either do the math at 96.00 grams per mole divided by our total, divided by 180.18 grams per mole. Right, so then the oxygen is going to be whatever that is. Oxygen is 96 divided by 180.18, 53.28%. Or you could actually just add these together to get about, 47-ish%, and then you get your 53% as 100 minus 47%, and that would give you your percentage of oxygen. Now, quick check, right? The percentages should add up to 100 because all we've got is carbon, hydrogen, and oxygen. So the percentages should add up to 100. And if we look at it, yeah, they look like they add up to 100. And the question that we were trying to figure out was how much of this tree comes from the air, from the CO2 in the air, and how much of this glucose comes from the water that it pulls in. And the answer is, somewhat surprisingly, because the hydrogen is the only thing that's coming from the water, it's only 7% of the mass of the tree. So 93% of the mass of a tree comes from its carbon and from its oxygen, from the CO2 that it's pulling in from the air. So, if you look out your window and you see a tree, most of that is carbon dioxide that it pulled in right from the air. This is why people plant trees, in order to offset carbon dioxide emissions, because the trees will lock in carbon dioxide as they grow. Okay. And you're basically taking the gas phase carbon dioxide and turning it into tree stuff. 93% of the tree stuff comes from CO2. Very, very, very cool. Yeah. That doesn't count all the water that's like in the cells and everything like that, which is the dry mass of the tree, not the wet mass of the tree. So that's kind of important. Okay, that's that one. And here's kind of the way that we figure it out. It's just what percent by mass is carbon, what percent by mass is hydrogen, and what percent by mass is oxygen. And this is how you get it from the molecular formula. You use the number of atoms times the atomic mass, and you divide it by the total molecular weight of the compound, which is exactly what we did back here. Right, here's the number of atoms, there's the atomic mass, you get how much the carbon weighs. Right, then you get your total, and then you're dividing these by your total to get your percentages. There's a neat little thing about the human body. Right, move this over. By atomic percent, we're mostly hydrogen because of all the water in us. By atomic percent, we're mostly hydrogen. But by mass percent, because oxygen is so much heavier than hydrogen, oxygen is 16 times heavier than hydrogen, by mass percent, we're mostly oxygen. And then the second one by mass is carbon, and then the third by mass over here is the hydrogen, 10%. So yeah, it's interesting to see the difference between mass percent and atomic percent for the human body. I always thought that that's kind of neat. That's it for the actual content. We're going to do another another sample problem. So I'm going to set up a sample problem for figuring out the percent composition, and then we'll finish the video. So here's the first sample problem that we're going to do. The first example is this one here in your textbook. Researchers have isolated a compound that contains only nitrogen and oxygen. They found that 4.6 gram sample, so that's the sample, that's the whole thing, of the compound contains 1.4 grams of nitrogen. Find the percentage composition of this compound. So all we need to do is the percentage composition, the percent nitrogen and the percent oxygen. So I've written down the facts here. We have just nitrogen and oxygen. We have a total of 4.6 grams. We know that nitrogen is 1.4 grams. Let's work out the percent nitrogen. Percent nitrogen is going to be the 1.4 grams, it's how much nitrogen we have, over our total, 4.60 grams total. And what happens when I do that? 1.4 divided by 4.6 is 30.4%. 34.4% nitrogen. 30.4% nitrogen. How about the percent oxygen? Well, we have two options. Percent of oxygen. Probably the easiest one is just because we know it's all nitrogen and oxygen, we can just go 100% minus the percent of the nitrogen, right? And shortcut. So it's 100% minus 30.4%. So we're going to end up with 69.6% oxygen. Okay, simple answer. So it's 30.4% nitrogen and 69.6% oxygen. And that's how we figure out the percent mass there. Then we're going to do another sample problem where we're going to use the formula. We're going to go from the formula. So we'll do a second sample problem. This one's going to be calculating the percent composition of calcium hydroxide. Given the formula here. And we want the percent composition. So we want the percent calcium, the percent oxygen, and the percent hydrogen. So let's jump over here. Here I've written out my formula. The first step is to figure out how many of each atom I have. So calcium hydroxide. One little hint here, you can actually just distribute the two in if you want. This is not a great way to write chemical formulas, but you can distribute it in and kind of rewrite it as CaO2H2 if you want. Sometimes it helps people visualize how many of each atom there is, right? Because the 2 is outside the brackets. It'll distribute in just like in math. So that means we have 1 calcium, 2 oxygens, and 2 hydrogens. So we've got 1 of these, we have 2 of these, and we have 2 of these, right? 2 of these, 2 of these, 1 calcium. So calcium is 40.08 grams per mole in my table. I'm just looking at my table to get these, right? I've got my table right here. So that's 40.08 grams per mole. The oxygen I know is 16.00 grams per mole, because that's in my table as well. It's up here, oxygen. And the hydrogen is 1.01 grams per mole. That's 32.00 grams per mole, and that is 2.02 grams per mole. All right, I need a total, so let's get our total. To do the total, I'm just going to add those up together. So let's do that. 40.08 plus 32 plus 1.01. 73.09 grams per mole. That's the total. And now to get the percentages, I'm just going to divide each element in turn by that total. So the percent of calcium is going to be 40.08 grams per mole divided by my total, 73.09 grams per mole. And that's my percent calcium. So that's 40.08 divided by 73.09 is 54.8% calcium. 4.8% calcium. For the hydrogen, for the oxygen rather, the oxygen is going to be 32.00 grams per mole divided by our total 73.09, so it's the same thing, right? It's the total because we want the percentage, 0.09 grams per mole, and that's going to equal whatever 32 divided by 73.09 is going to be 43.8% oxygen, 43.8% oxygen. And then the hydrogen down here, you know, you got two options. You can go 100 minus these two together, or you can just do the percentage of it, 2.02 grams per mole, divided by the total, 73.09, always the total, 73.09 grams per mole, and that gives me 2.02 divided by 73.09 is 2.8% hydrogen, 2.8% hydrogen. Then we can do our little self-check, right? The self-check would be, do these add up to 100? Because if they add up to 100, we know we've done things correctly. So I'm going to add these together. 2.8% hydrogen plus 43.8% oxygen plus 54.8%. I get 101. Where did I go wrong? I got 101.4%. So I think I got something wrong somewhere. Let me check my total. I think I might have screwed up my total. 40.08 plus 32 plus 2.02. It's 74.1. I put in something wrong. I must have put in something wrong. It's 74.1 grams per mole. 74.1 grams per mole. Not a big deal. 74.1 grams per mole. I'm going to fix my total here. 74.1. 74.1. 74.1. And that's going to change my percentages. So let me put in my percentages again. By the way, I didn't mean to do that. That was actually a completely organic error. I screwed up something on the calculator, and now I have to fix it. But thankfully, now that I fixed it, this is 54.1%. I'm just dividing it. 32 divided by 74.1 is 43.2% oxygen, and 2 divided by 2.02 divided by 74.1, 2.7% hydrogen. Okay, that should be a little bit better. Let's see if that actually works. 24.1 plus 43.2. Alright, I'm adding these, this plus my 2.7. I get, there we go, 100. I get 100%. So yes, this is the correct one. 54.1, 43.2, and 2.7%. So that's the percent composition of my calcium hydroxide, and that's how we go through one of those problems. So yeah, you'll definitely be seeing questions like this on a test. So definitely worth it to know how to do it. And if you do any analytical chemistry, you might actually end up doing some combustion analysis and doing it as natural problem, right? This kind of stuff, the combustion analysis. That's it for today. Thanks for paying attention, and I'll see you guys in class.